Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's an honor to have Sven Sukin with us today. Sven is a repeat intern, also an MSR fellow, as well as a Fulbright scholar, working at Harvard University in what we all believe is his last year of his dissertation work before he goes off to become a professor somewhere in the world, hopefully not too far away from where we are, because we like collaborating with him. He's been working with David Parks and David Parks' team at Microsoft Research. He's been working with Kamal Jain and Mary Czerwinski, Desney Tan, and myself over the last couple of years. He's been particularly interested in electronic market design, the application of mechanism design and game theory to electronic markets and systems. He's taken a particular interest in a very interesting area that tries to join the complexities of markets with potentially naive consumers who don't understand the details of how markets actually work, looking at concepts like what's the user interface experience with markets and how do people control complex markets, what's the implications of hidden aspects of markets from people. In his recent internship work, which he'll be talking about today, he's been exploring more aspects of how UI design and optimization meet markets, and you'll be hearing more about that right now. So it's an honor again to have him here today, Sven, on market design meets user interface design.
Yeah, thanks very much for this wonderful introduction, and it's great to be back here. And I'm going to be talking today about the work I've done last summer with Eric, Kamal, Mary, and Desney on market design meets user interface design. And I want to start with this little example to motivate what we've done. So this is just a capture of a cafeteria salad bar. And research has shown that just by rearranging the food choices in a cafeteria, we can increase or decrease the consumption of certain food items by up to 25%. This is a website I just discovered yesterday where users go online shopping, and instead of browsing through all the possible laptops out in the world, this website only gives them exactly one laptop. And they can't do anything else but buy this one laptop. So we're taking all choices away from them. And many users are happy with this website. This is another example about 401k plan design, where researchers, economists have shown that giving employees more choices in the plan selection actually leads to fewer enrollment in the first place. So we have these kind of contradicting results according to standard economic research or theory. And Thaler and Sunstein have captured this contradiction quite nicely by making these distinctions between humans and econs. So on the one side, the econs, which the economists usually talk about, are assumed to be perfectly rational, have unlimited time to make a decision, and unbounded computational resources for deliberation. However, we're dealing with real humans in the real world, and these humans have cognitive costs. They have bounded amount of time, and in particular, they have opportunity costs for doing something else than deliberating about the problem at hand, and they have bounded computational resources. So as a consequence, while the way in which we offer choices to an econ doesn't matter, this actually matters a lot for humans. And Thaler and Sunstein call this the choice architecture matters. And in this particular project, what we looked at is how can we design the choice architecture for an electronic marketplace. And this is nothing else but electronic market design for real humans instead of for econs. Okay. Here's a brief outline of my talk. Next, I'm going to dive a little deeper into this intersection of user interface design and market design and motivate why I think it's an important field of study. And then I'm going to motivate one particular problem that we looked at and where we situated all our research in, which I call the 3G bandwidth allocation problem. And then I'll show you in detail an economic experiment that we designed and ran over the summer and all the results that we have from the statistical data analysis. And if I have time, I'll give you a little bonus chapter on a hidden market with fixed prices that we've started to think about recently. And then I'll conclude. Okay, here I'm depicting this intersection of user interface design and market design. And I want to motivate why user interface design is really important for markets for at least 4 reasons. First of all, the UI is the first point of contact for any user interacting with the market, and it will decide whether the user even stays in the system or goes to another market. But more importantly, the UI design constrains the kinds of market designs that we can usefully employ. And the user interface defines how the users express their preferences in the market, depending on how what kind of choices we give them, whether we let them enter values or move sliders. This defines how we learn about the user's preferences. And last but not least, and probably most importantly for our talk, the user interface defines the amount of cognitive costs we put on the user. How complex is this UI and thereby the market for the user? So in general, we'll have this trade-off between a more complex market or UI on the one side and a more expressive market on the other side, and we'll have to decide where the sweet spot lies. Okay. So in our research last summer, we introduced this new paradigm thinking about market user interfaces. And I think this is best defined by these 2 questions, namely, which information do we display to the user about the market at any point in time, and what choices and how many choices are we offering the user? Okay. And the research question we were interested in is, what is the optimal market user interface given that users have cognitive costs and are not perfectly rational like the econs? Okay. And here is what I think one of our main contributions is essentially a methodology to optimize market user interfaces. What we start with is a particular market user interface, like a dummy interface, and then we run a user experiment on that dummy. So what we did is we designed a market game that we let the users play, and because we designed the game, we knew which choices were optimal at any point in time, and we could measure users' performance and compare the performance with the optimal play. Based on this experiment, we could then feed the results into a learning algorithm which gave us a user model predicting future behavior of our users in similar environments. So based on the experiments from here, we learn and then build a user model. And then we can put this user model into an optimization algorithm and essentially search over the whole design space for the user interfaces. For each design, we compute the expected value based on this user model, based on the real human behaviors, and then we choose the design with the highest expected value, and leading us to the optimized market user interface. Okay, so this is the abstract view. Let me make this all a little more concrete by diving into this particular application. Yes?
It seems you're optimizing for the user, not for the guy who's selling to the user, which is usually how websites are designed.
It's a good question. And let me answer yes and no. We are interested in this talk mainly about overall efficiency, which is defined as the sum of all users' utilities. It is true that if you are concerned about maximizing the revenue of a business or of a website, you might design the choice architecture differently. In many markets, in particular in very large markets where you have competition, usually you want to have a very high efficiency in that market as well, because if you lose too much efficiency, another competitor can come in, design a more efficient market, and users will switch. So that's why in recent years, many economists have argued for efficiency being a good reason to optimize, a good point of optimization. Okay, so the particular problem we looked at as a motivating example is that of 3G or 4G bandwidth allocation for smartphones. So there is currently a shortage of this bandwidth, and one sign is that AT&T has recently dropped their unlimited data plan. And there are multiple reasons. One is we have exponentially growing number of users, but at the same time, it's very expensive to improve the existing infrastructure. And demand actually has high variance. While supply is fixed, there's always, tomorrow there's going to be the same supply of that bandwidth as today. But depending on the time of day and the location, the demand that users have for this bandwidth is highly variant. I mean, in New York or San Francisco, it's almost impossible to get online. And in Denver, it's probably not a problem. And in particular, the time of day plays a big role in terms of what the demand is. The current approach for solving this shortage is simply that whenever there's more demand than supply, we simply slow down every user. Or even to prevent this from happening, we simply constrain the total data usage of every user so that every user just consumes at a very low level. Okay. Obviously, this introduces large economic inefficiencies, and we believe we can improve the system by going to a market-based solution. So the assumption is that sometimes users are doing tasks of high importance, sometimes they're doing tasks of low importance, and users might be willing to accept a lower performance now when they're doing a task of low importance, like they're just updating their Facebook status, if we can guarantee them a high performance later, perhaps when they are emailing an important presentation to their boss or something like this.
Why did you make that assumption?
We'll make that assumption essentially to make this point. Let me please ask again if this doesn't make it clear. So what we want to do is we want to shift the usage of some users to a different point in time. So whenever there is too much demand, and if this is the maximum supply level that we have in this market, we need some users to stop consuming and consume at a later point in time when there's enough supply. So if I can convince some of these users to not consume at all or to consume at a lower rate, then I'm fine in this market. So this is why we need this assumption that some users will be fine with sometimes consuming at a lower rate if we can guarantee them a higher rate later. Okay. So the idea is very simple. When we have more demand than supply, we will ask users to interact with some kind of market user interface with a bandwidth market, and then we update the prices to balance demand and supply until we come out fine. So by the way, this raises some interesting net neutrality questions because we're no longer treating every package equally in this market. However, it is actually in line with recent agendas of researchers on the net neutrality question because we're not giving the provider the power of deciding who do I favor, but it's the user who we put in charge. Do I want to have slow or fast internet right now? And that's actually in line with some.
And then just for the question, I mean, it was a good one. Keep in mind that this is there's a domain that was selected here for doing the studies as a sample domain, but the principles and the ideas can apply to many different kinds of domains where we hold different games we're playing for different assumptions.
Fair. I'll wait till everything's over. Because this domain I'm particularly interested in.
Okay. Good.
It's a very challenging domain.
Yeah. Thanks. Ece?
If we have classes of memberships, one being very prior to membership where you get the supply whenever you are, and there's medium membership where you get the data whenever available. So, and you, with the market structure, you assign different prices in different locations for these different classes dynamically. How would a system like this would compare with that? Because in that system, you are not doing the auction every time you need something, but you have a pattern and you make decision maybe monthly, maybe when you are become a member.
Yeah. I think to answer that question, definitely you would have to write down a formal model and state the assumptions clearly. Obviously, by having a tiered pricing system, you can remove some of this problem. Essentially, the people are not. What you're doing is you're making the people who are not willing to pay much to simply consume at a lower rate, and the people who are willing to pay a lot, we allow them to consume a lot. And that's what some of the cell phone providers are doing right now. We have tiered pricing being introduced by Verizon, for example, a month ago. Or I think ideas of that for 4G. So your idea is being rolled out on Verizon. But that idea would still lead to certain economic inefficiencies. Namely, if you are a customer who is, let's say you chose the low tiered pricing, and there is currently enough supply so that we could allow you to consume at the full speed, but we don't allow you because you chose the lowest tier, right? And that's losing efficiency, that's losing social welfare. And our approach would avoid that. Okay. So here's a sample UI, what this interface for this market could look like. We didn't actually build this on a phone, but this is how I could picture this. Let's assume a user gets 50 points a month that he can spend, and you don't have to interact with this market at all whenever there's enough supply for everybody. But whenever there's a shortage, let's assume every 3 days, you get this little pop-up and you have to decide right now, okay, do I want to stop surfing, or do I want to keep surfing but at a low speed? I'm going to pay 2 of my 50 points. Or do I really need full speed right now because I'm doing something really important? I'm going to pay 10 points. Okay, this is what this UI could look like. You look at this, you think about it, you click, and then you continue what you did before. So what can we change about this market UI? Well, there's a couple things we can change. And we considered 4 different UI design levers. The first one is really the easiest one. How many choices should we offer the user? The second one is, should these prices that we're offering the user be fixed, or should they change over time? The third one is, do we have fixed or situation-dependent choice sets? What this means is, do we always, if we decide we're going to offer the user 4 choices, do we always give him the 4 same choices? Or do we give him different choices depending on the context that we think he's currently in? And then last but not least, this is the question of how do we optimize the UI? If we have some model of user behavior, we can optimize the UI either for perfectly rational behavior, or we can optimize the UI assuming that the user is sometimes going to make mistakes. And we're going to analyze all of these design levers in our experiment. So now I'm going to move on to describing the details of the experiment and then to our results. So let me show you a quick demo of the game that we designed. Here we go. This is not the game. This is just my way of starting the game. And so here we go. This is essentially the application I wrote to run the experiment. It is the game where we're showing the user, similar to the screenshot you saw before, 5 choices, and every choice has a speed. This is 0, 100, 200, 400, 900 kilobytes per second. Every choice has a price in tokens from 0 to 18 tokens. And in contrast to the real application in this game, we also show the user the value of that choice, going from minus $1.2 all the way up to $1.7. I'll explain that in a second. Okay. We give the user 30 tokens that he can spend over 6 rounds. Every decision he makes is 1 round. Whenever the user clicks on one of these choices, we're going to subtract the number of tokens from his total amount of tokens, and we're going to add the value of that choice to his score. So this is essentially describing how valuable is getting 900 kilobytes per second to me in that particular situation. And so we're defining that value for the user. So let's assume the user clicks here. He gets to the next round, 5 rounds left. We subtracted 8 tokens, and we added $0.9 to his score. And what happened randomly, there was chosen a new distribution of values in this round. The values keep changing. Just in the last round, we had minus 1.2. Now we have minus 0.7. So now the user has to make another decision. And he has to essentially allocate his tokens, the 30 tokens, over the 6 rounds that he's playing. If he runs out of tokens too early, he will at some point no longer be able to choose to make a selection from these upper choices because they're too expensive. He can't afford them anymore. And then he will be forced to take these choices that have a negative value. And at some point the game is over. We show the user what his total score was, in this case 70 cents, and we show him his accumulated score overall. And it's important, this is very important, because what we actually did is we let the users play after an initial training period and detailed explanations. We let them play about 50 games, and we paid them the total amount of money they made in all of these games together. And I think the maximum payoff was around $40. The median was around 20. Okay. So I explained the basic structure of the game. In the upper left corner, we have this timer that's ticking down, and that is putting a time constraint on the user. And that was important for our experiment because remember, we are studying markets where cognitive costs shall matter. So we have to limit the amount of time that the user has to make a decision. Otherwise, he could just solve this game optimally on paper, which we didn't want. So we had to put him under some time pressure. And in the fixed time constraint, later we put him either under a 7-second or 12-second per round time constraint. This task category that we're displaying here is essentially a key for the user about the distribution of values that he can expect. And before the game starts, we show him a little table, and he has time to look at this table. He doesn't have to summarize this table, but essentially to build a model of what to expect when he's playing the game. And he sees, okay, if my task category is high importance, this is the distribution of values I will see in the game. For medium importance, this is what I will see, and for low importance, this is what I will see. And we also show him the 5 different choices he gets in the game and the different prices he can expect over the course of the game. Yes?
If something's of low importance, why would it be more harmful to have only 100 kilobits per second for it than for high importance?
Time out. Something is of low importance. You mean this minus 0.5? Yeah, that's it's a good point. It's not, the semantics of low, high, and medium importance was essentially meant to. We could also call this blue, red, and green, and give the user 3 signals about different situations he could be in or different value distributions he could expect. What we did is we generated a utility curve, and then at some point these utility curves for the different classes of importance would cross. So they had to, at some point, they had to cross and overlap. So I agree that there's a semantic inconsistency in this little point, but I don't think it mattered too much for the experiment. Okay, so let me get back to this. So this was the game that the users played so here is the real time limit that they saw, 7 seconds per round. When they ran out of time, they got a warning 3 seconds before the end of the round. The computer would start beeping, and we told them beforehand if they don't make a selection by the end of the 7 seconds, the computer automatically selects the lowest choice for them, which is often not the best choice. And so they had to avoid that by all means. Okay. So I already told you to study cognitive costs. We made the game challenging enough so that it was actually not easy to always find the optimal choice. That's why we designed this multi-step optimization game, and we put the users under time pressure. The first time constraint that I've shown you is this exogenous time constraint where we fix the time limit per round, and that was in our experiment either 7 or 12 seconds. But we also had a second time constraint, which I call endogenous, where we give the user 4 minutes overall to play an unlimited number of games, meaning once the user finished 6 rounds, the game ended and the next game started. So now the user had the challenge of deciding, okay, how much time do I want to spend on each decision? But the longer I spend on each decision, the fewer games I get to play in total. So the decision time was now endogenous to the overall meta-game. And I told you to provide the users with the proper incentives. We showed them the value of each choice and paid them based on how well they did in the overall game. Okay. So if you're familiar with Markov decision processes, then you've probably already noticed that the game we designed is essentially an MDP. We have the state space consists of the current budget that the user has left, the current round, the current values of the choices we're offering the user, and the current price vector. And the action space is simply which choice do we give the user, which choice does the user select, and the transitions are deterministic for the budget and the round, and they are random for the values and the prices. And if I didn't mention this before, in every transition from one round to the next, there was a 1 in 3 chance of any of the 3 categories of showing up, the high, medium, low importance, and a 1 in 3 chance of one of the price levels showing up. Okay. What we did is for any of the games that we let the users play, we solved the game optimally, solving an MDP. Thus, for each situation that the user could face, we computed the Q value of each action, Q of A. And the Q value is just the terminology of for every action in a particular game, meaning if we had 4 choices, for each of the 4 choices, we compute the optimal expected value of taking that choice now and playing optimally for the rest of the game. Okay. So it's the strongest finding from the data, which was also which is very positive, is that users understand and properly detect these Q values. So how this shows up in the data is that we have a very high correlation between the Q value of a particular action and the decision that the user actually made. 1 second. So in particular, the users are not myopically going for the highest value of the 4 choices that we're showing them, but they are looking forward, okay, how expensive is that choice now? How many rounds do I have left? So they're actually properly planning forward given the uncertainty of the game. Yes.
Are these users MIT students, or are they typical members of Eurasian?
We recruited 60 people from the Seattle area, and none of them were computer scientists, or we excluded people with a math, physics, economics, statistics major, no user design experienced people. So basic skills. Once in a while, I think out of the 60, I had 1 finance major because I forgot to exclude finance from the setup. But most people had a very base level. But all of them had a college degree, at least a bachelor's. So we wanted people to at least understand what it means for a choice to have, a 1 in 3 chance or something like this.
Keeping in mind, I know of at least one study that shows that decision analysts are the worst decision makers.
Okay. Yeah, Nikhil?
So did the optimal Q value have any structure, have any simple structure in this case?
That is a good question. And we tried to design the game such that it didn't. When I started designing the game, I went through a lot of iterations. And at the beginning, I came up with games where it was very easy to see which one was the optimal. For example, when I had a game with 3 choices and I had 3 categories, it was a simple mapping from, the high importance category was always choose the top choice, the medium, the middle choice, the lowest choice. But I kept changing the value curve, and I kept introducing uncertainty in terms of prices going up and down and values going up and down, such that there was no longer an easy mapping. Okay, so to make the game challenging enough. And the results show, if there were an easy mapping, users didn't detect it, but there wasn't. Yeah. So let's first look. So I told you that these Q values are highly predictive for users' value. Let's look at this in a little more detail. The first thing I'm looking at is games that had a fixed time limit, and I'm doing a binary logistic regression on the variable opt choice. That is, did the users make the optimal choice among the set of choices or not? So it's a binary variable. That's why I'm doing a binary logistic regression. And what we're seeing here is the Q value difference between the top 2 choices. And we're showing it shows up as highly significant in terms of predicting this binary variable opt choice, so p less than 1,000. And as long as this term is larger than 1, you have a higher probability of selecting the optimal choice when this value goes up. So the fact that it's over 100 means it's incredibly predictive in terms of making the optimal choice. So the larger the difference between the first best and the second best choice, the larger the difference in Q values, the higher the probability that the users found the optimal choice. Which intuitively makes sense, because when the Q values of the 2 top choices are close to each other, it's not easy to figure out, okay, which one is really the best. And the larger they are apart from each other, the easier it is to see. Yes?
So did you have a dummy variable for every participant?
Did I have a dummy variable? No. What I did is I took all the... are you worried about...
the fact that these are not independent variables.
Right. What I did is I took all the... for efficiency, I demeaned all the values. So let me think about what I did there. For efficiency, I demeaned all the results and compared the variances to take care of that. For this effect, I think you're right. I didn't do that yet. So what you're worried about, that this statistically that this measure is actually it's not the right one.
Participant who was brilliant, and none of the other participants, and because you're counting these non-independent events, you may be overstating your significance.
Yeah, let me think about this. Yeah, I think you're right. I have to do that. I have to go back to that analysis and introduce a dummy variable or do a repeat measure analysis. I think that's
just compare the means. I mean, they should be far enough. They should be far enough off from random that you can prove they're statistically doing better than random. I think it's the same thing you're getting here.
Right. So when I look at on the next couple slides, when I go to efficiency, then I looked at the means, and then that effect doesn't, and then that doesn't show up. I think here I could do the same thing. Yeah. So it's a good point. Let me move on to decision time. The worry is that this. When we look at the means instead of when we take care of the fact that we had multiple non-independent results here, that this statistical significance will drop. However, that was so strong, and I looked through the data in detail that I have high confidence that even if we look at the means, the same result is going to come out. Now we look at what happens with decision time as we look at the Q values of the different choices. And so what here we're doing a linear regression on the dependent variable time taken per round. So now we are no longer looking at the games with the fixed time limit per round, but where they had an overall time limit of 4 minutes. And here what we're seeing is that the Q value difference, again, highly predicts the amount of time taken for a decision. Essentially what this is saying is if the Q value difference goes up from 1 to 2, the users take, on average, 3.5 seconds less to make a decision. And I think the average decision time was somewhere between 3 and 6 seconds, depending on the particular game they played. So higher Q value difference, much easier, much faster to make a decision. Okay. Now that we've seen, the Q values are the highest, most important predictors for users' decisions, let's move on to the 4 user interface design levers. So this was our overall flow that we wanted to follow. And here we studied with the first experiment where we had 40 users, the first 2 design levers, where we varied the number of choices and we varied whether we had fixed or changing prices. Based on the data from these 2 experiments, we did the re-optimization. And then in the second experiment, we tested, what was the effect of optimizing the UI for optimal or suboptimal users? And what was the effect of having fixed or changing choice sets? So we'll start with these 2 design levers in the first experiment. So here, this is a game with 3 choices, where I'm offering the user 0, 200, and 300 kilobytes per second. And with 4 choices, I'm offering them 0, 100, 200, 400, with 5 choices, and this is what it looks with 6 choices. So the users play different games with more choices. And the choices were optimized such that I searched through the design space and I found those 4 or 5 or 6 choices that were optimal, given that I needed to give them 4 or 5 or 6 choices. So now let's look at what if we compare this. The optimal value obviously keeps increasing as we give the users more choices. That's of course the more freedom you have in making decisions, the better you can be overall. But the error rate of our real users playing also went up, which is expected. With more choices, you can make more mistakes. So also the value loss per game keeps going up, but that is relative to the maximum amount you could possibly make. So let's see if these error rates are statistically significant. If we again run the binary logistic regression on the optimal choice variable, we see that giving users more options made them less likely to find the optimal choice. And that is statistically significant, with the caveat that I have to do the demeaning. So that effect is important. So what happened to overall efficiency? This is really what we're interested in. And this is the resulting graph. Blue is the optimal value of the game, which keeps going up as we increase the number of choices. And red is the curve that the users actually achieved. The value keeps going up as we increase it from 3 to 4 to 5 choices, and then goes down as we go to 6 choices. So this is the curve that we had hypothesized would happen, that at some point, giving users more expressiveness, overall efficiency actually decreases. Unfortunately, these results are not only statistically significant going from 3 to 5 and 3 to 6, but this drop here is large enough to be statistically significant. So that's unfortunate, but it happens. We only had 20 users in that particular experiment. I believe, either we need more users to get statistically significant effects, or we add a fifth category with 7 choices or 8 choices. At some point, we're going to see this effect clearly, that adding more expressiveness for the users is going to actually decrease efficiency. Yes?
How much of a problem was it? The 6 choices were one long row on top of each other instead of 2 by 3? Seems to use real estate a bit better.
I agree. It's a long list of choices, but the users we trained them for about half an hour on the game, and they had a mouse, and it's really easy enough to find you don't need 5 seconds to move from the top to the bottom of the screen. So I don't think that was the problem. I actually thought about keeping the size of the game constant and changing the size of the buttons, but that would introduce other problems with changing sizes of the buttons, and so I decided to keep this that way. Okay. So yeah, as I said, this is the curve that we had predicted. Unfortunately, this drop at the end didn't come out statistically significant, but nevertheless, this is the curve we got. Okay. Let's look at the second design lever, fixed or changing prices. So what this means is, when we had the fixed prices condition, then for the same choices, 0, 100, 300, 900, we would always have this price, 0, 2, 6, and 18. When we had changing prices, then we had these 3 different price categories. When we're currently in the cheap world, prices would only go up to 9 tokens for 900 kilobytes per second. In the medium, they would go up to 18, and in the expensive world, they would go up all the way to 27. So now every round, one of these 3 levels would be chosen at random, and users had to cope with that. So what happened? Let's look at the error rate again. First looking at the games with the fixed time constraint. And here we see that by having changing prices, so this is now a binary variable, whether we had changing or fixed prices. If we had changing prices, the probability of finding the optimal choice actually decreased. So this value is less than 1, so there was actually a drop in finding the optimal choice. And that drop is slightly stronger than the corresponding term for the number of choices left. So what this means is having changing prices instead of fixed prices has a slightly more negative effect than giving the user one more additional choice in terms of what's the increase in making an error on the user's part. Okay. So let's look at what the effect of changing prices is on decision time. Now we're looking at the games with the 4 minutes overall time limit. On average, the users took 4.8 seconds to make a decision. And now we're doing, again, a linear regression on the time per round that the users have taken. And here we're seeing that when we have changing prices instead of fixed prices, the users take approximately half a second longer to make a decision than with fixed prices. And half a second, is approximately 10% of the average decision time they take. So it takes them slightly longer to reach a decision, and as we've seen on the previous slide, they make more mistakes. Okay, so this doesn't say anything yet on the resulting effect on efficiency, and I'm postponing this to a later discussion because analyzing efficiency with changing where this fixed price is actually tricky because it changes the market structure completely, and you cannot analyze efficiency in isolation. What you have to, because it's not possible that all users at the same time, everybody chooses the high speed or everybody chooses the low speed, which would happen if everybody would react in the same way to the changing prices. So to analyze the efficiency, you essentially have to build a market model and consider the effect of what happens if a whole economy now is facing fixed or changing prices. So I'll get back to that later. Okay. Now moving on to the third design lever, whether we had fixed or changing choice sets. So the problem is we don't know users' values in the real world. When they're facing a decision, they have these 4 speed levels. We don't know, what's your value for 300 kilobytes per second. But every choice the user makes is a signal about the user's value to some degree, because we can learn a mapping from the current context the user's in to a value estimate. So if every time the user is currently in his Facebook application and we present him this UI, and every time he selects the lowest choice, then we can learn something from that about an estimate of the user value whenever he's on Facebook. Whenever the user is currently in Outlook trying to send an email and we present him these choices and he selects the full speed, this is another value estimate that we learn. So if we take these learned mappings and present the users with a situation-dependent choice set, then we end up with something like this. In an ideal world, if we know, okay, currently a low importance task, or another word for this would be Facebook, let's give the user these choices, 0, 100, 200, and 400 kilobytes per second. Medium importance task, we give him these choices up to 600. And high importance, we give him the choices all the way up to 1,000. Okay? So now we're optimizing the choice sets for the situation that the user finds himself in. Okay. What's the effect of this on efficiency? Doing a linear regression on efficiency, what we find is efficiency increases slightly, but statistically significant when we have changing choices compared to fixed choices. By almost 0.1, which is a non-negligible amount. Let's look at this in a little more detail, what actually happened. So when we redesigned the UI, went from fixed to changing choices, what happened is that we actually changed the optimal value of the game, but only slightly so. We increased the optimal value by only 0.02. However, the realized score of our users increased by 0.08, so almost 4 times as much. So having these changing choices, the users did not only exploit the efficiency gain that was there because we changed the game, but it was actually easier for them to find the right choices and to make better decisions. So changing choices actually helped the users to achieve higher efficiency. And that wasn't clear a priori. I remember Eric and I had this discussion whether presenting users with different choices every round, every 7 seconds you get different choices, and you have to rescan the choice set and look at, okay, what am I facing now? This might actually make things worse because it's confusing users or slowing them down. But this shows it actually helped them make better decisions. Okay. Now, the fourth design lever where we move to the UI optimization part. So to remind you, based on the first 2 experiments, we took the data and trained this user model to have a predictive model about user behavior in other environments. And then we searched for the optimal user interface given this user model and came up with an optimized market user interface. So now we're going to look at this part of the experiment. And here's what we did in this learning and user model building phase. We've already seen that the Q values are the most important predictors for users' behavior. So we took this softmax activation function to have a value proportional error function. So this probability distribution is telling us what's the probability of choosing action A given the Q values of AI and the Q values of all the other AJs. And if you order the actions by their Q values, you get something like this, that the action with the highest Q value will have the highest probability of being chosen, and so on. Okay? Oops. So in the learning and model building phase, what we did is we computed the maximum likelihood estimate of the model's parameter lambda to fit the data from the first 2 experiments. And then in the optimization phase, we searched through the whole UI design space and selected the best user interface, and best meaning achieving the highest expected efficiency over all possible games. And we did that 2 times, once assuming optimal play that resulted in a UI optimized for optimal players, and once assuming suboptimal play based on the user model we had learned in this phase, assuming suboptimal play. And then we ran an experiment with both UIs, looking at, okay, how did users perform with one UI and how did they perform on the other UI? Okay. So here are the results. Let's first look at the error rate again, running the logistic regression on the optimal choice. And what we see is that if when we optimize the choices for suboptimal play, the probability of getting the choices right actually increased, and statistically significant so, and by a non-negligible amount. As long as this is larger than 1, the probability increased. So with the UI that was optimal for suboptimal play, the error rate was lower than with the UI for optimal play. So that's good. But what happened to efficiency? This is what we're ultimately interested in. And here we're running a linear regression on the dependent variable efficiency. It was actually the expected realized score demeaned. And here we're seeing this very surprising result that efficiency actually went down, minus 0.1. And that is also a statistically significant result. So that was really surprising when we first saw that. And obviously, it seemed to indicate, okay, our method totally didn't work. So we achieved lower efficiency with the re-optimized UI. And even though on the previous slide I showed you that users made better decisions among the choices we gave them, we still got overall lower efficiency. So let's look at what happened, because the problem is there were actually 2 counteracting effects in this re-optimization phase. And here is a table where I'm looking at the mean values of the achieved scores. First, let's look at the optimal value of the game. When we optimized the game for optimal play, the game had an optimal value of 1.02. And when we re-optimized the game, the optimal value of the game decreased to 0.78. So we took away about 20% of the efficiency from the user. And the user never had a chance to recoup these 20%. So these are gone. I mean, in this game, you can't achieve more than this efficiency. Why did we do this? Because we thought that playing this game was so much easier that the user would actually achieve a level here that was still better than a level that he would achieve here, because this game would be a more difficult game to play. Okay, but what actually happened is that the realized scores look like this. For the game optimized for op, the users achieved 0.42, and optimized for sub-op, they achieved 0.32. So what we're seeing is that the value loss compared to the optimal value of the game was much smaller here, which is consistent with the fact that the users made fewer errors. However, unfortunately, the overall efficiency was still lower than here. So what this is saying is that these 2 counteracting effects, the effect that we took away some efficiency from the user in the first place was actually stronger than the effect that we made the decision easier for the user in the second place. So overall, we took away too much efficiency in the re-optimization phase. Or in other words, we didn't find the right sweet spot. So there's many explanations for why. We only trained a user model based on 20 users from the first experiment. That's not a lot of data. That was perhaps with a richer data set, we could come up with a better user model that was had better predictions for user behavior. Or perhaps we forgot some important variables that are crucial for user behavior. And one of those might be loss aversion. And this is, so what we looked at to illustrate what loss aversion means is when the user plays the game, sometimes the user has to, okay, this is impossible to see. Okay, sometimes the user has to take a negative value now to save his tokens so that he can get a higher positive value in a later round. What loss aversion means is that the users are too averse to these negative values and try to avoid them by all means, and might be willing to spend a very high amount of tokens now just to avoid taking this small cut of $0.3 now. And obviously that would lead to many suboptimal decisions. Okay. So let's look at the regression. And what I did is I looked at the logistic regression for the optimal choice variable again and compared it. What happened, how does the effect whether the optimal choice had a positive value or a negative value affect that? And indeed, users were more likely to choose the optimal choice if it had a positive than it had a negative value. So the takeaway from this is perhaps that in a next iteration when we're running a similar experiment again, we would also take, so that wasn't even part of our predictive model, the fact whether the values had negative or positive values. That was the optimization algorithm was completely ignorant about that. It would only look at the differences in the Q values. So perhaps if we take something like positive and negative values into account and build a richer user model of behavior and then do the experiment again, we can come up with a better result. Okay. Another interesting fact that I found in the data is the role of the time. And it seemed that users were overconfident at the beginning of a game and started making better decisions towards the end of a game. And by game, I don't mean the whole like 45 minutes that we let them play, but every game out of the 50 games, it seemed that at the beginning they made worse choices than at the end. So if you look at the current time step, then you see that the larger the time, and time step goes from 1 to 6. So that's essentially the round in the particular game. The larger the current time step is, the more likely you are to make the optimal choice. And this is not simply due to the fact that in later rounds of the game there were fewer choices, so you automatically made better choices, because we're controlling for the number of choices that were left. And we're controlling for the budget that's left and Q value differences, so this is a separate result from that. Okay, so in the early rounds, users are more likely to make mistakes, and that's why I called this overconfidence at the beginning. Yes?
One challenge with the MVP is that at the beginning of the game, it is looking 6 steps ahead to make the optimal decision. But at the later rounds of the game, this is the MVP approach is looking 1 step ahead and 2 steps ahead. So this result may easily show that people are looking ahead fewer than the MVP approach would do, just looking like a myopic, more of a myopic approach of looking 1 step ahead and 2 steps ahead. Which means when the look ahead is larger, the people's decision making doesn't agree that much with the MVP approach. But look ahead is an important issue there.
Yep, that's actually a very good explanation for this effect. Yeah, and I'm thinking about how we can tear this apart, how we can look at if this is another analysis I could run to figure out if that was the effect or not. But that is certainly an explanation for this effect showing up. Yeah.
There is some literature work showing that people are not looking very much
right.
ahead.
I mean,
like
yeah,
people are mostly myopic. So
yeah, of course. I intuitively believe people are more likely to only plan ahead 2-3 time steps than 6 time steps. Yeah. Yes.
So can you repeat the difference between number of choices left and current time step?
Yes. So number of choices left is the describes I ran this analysis on every decision for every round. So for every round there were, if we consider the game with 4 choices, there were either 4 choices left or 3 or 2 or only 1. So we saw previously that the number of choices left has a high is obviously very important for the
only 1 choice left is the optimal.
Yeah, then it's optimal, right. So the more choices there are left, the less likely you are to make the right decision. So if this value is less than 1, you're less likely to make a decision. So the higher the number of choices left, the less likely you'll make the optimal choice. So that makes sense. Right? With 100 choices, there's more ways to make a mistake than with only 2 choices left. And I'm saying that because I'm controlling for the number of choices left, and current time step still shows up as statistically significant. It is not simply, towards the end of the game, because you're running out of tokens, it was always the case that in the last couple time steps you had fewer choices left than at the beginning of the game. But this is not simply picking up that because I'm controlling for it.
You're controlling for it linearly, or how are you defining that variable?
It's in the, it's a binary logistic regression where all of these variables enter into the regression at this, together. So it's a logistic function over all of these together. Does that make sense?
Right, but my performance with my chance of making an error with one choice left is not half of my choice of making an error with two choices left. So if you're doing this as a linear regression on that variable, what you see in current time step could just be the what's left after that error results.
I don't think I fully understand. Note that this is not a linear regression, right? It's a binary logistic regression on the
it's binary on the
yeah.
on the dependent variable, but the question is what is the value you put before each of, in what structure is each of the dependent variables? Are you treating them linearly? Do you treat them as squares? If you're treating them as linearly, then a 1 would be half of a 2. But your chance of making an error when there's only one choice left is not half of your choice of your chance of making an error when you've got two choices left, because it's 0 and there's some error that's greater than twice 0 when you've got two choices left. So you can't just, it's a little premature to assume that because you factored in number of choices left, that's not what's going on in current time step. Because linear does not perfectly model its impact.
Yeah, what I think I understand the counterexample with when only one choice left, then you can't simply read that value up and use that. But I'm wondering what's the analysis I would have to run to make sure that didn't happen?
So he's measuring error on a single step, right? Whether a single step was errorful or not the total error in the outcome of the sum.
Right. So there's different each of these variables represents a different contribution to the error. Right. Now, the assumption is because your number of choices left is going to remove any part of the error that's being made that's a result of the number of choices. It reflects how many choices the user has. And so by having that variable in there, you're going to factor that out of at the end of on the last step, maybe I only have budget left so that there's one. Maybe the reason why I'm doing so well in the last step is because there's only one choice. So there's only the optimal choice to make. So if that is the case, when you've got this linear variable number of choices left, it doesn't properly represent the possible chance of error.
I see. So are you suggesting, for example, to instead of using letting number of choices left enter linearly into the binary regression, let it use 3 dummy variables for whether number of choices left are 4, 3, or 2?
I'm not sure what the right way is to fix it. I'm just pointing out that you may still have a confounder here.
Yes.
You can't assume that you've removed it.
Now I understand, and
I would take offline exactly.
Very intricate, yeah. But I think I might be able to fix that with introducing dummy variables for the number of choices left. Yeah, that's a good point. Okay, and so this essentially concludes the experimental results on the study that we ran. And now I'm going to briefly talk about an idea that we started to develop recently.
Any more questions on the first project first?
Do you want to ask now, or do you want to?
Any more questions on the?
I only have 2 more slides, then I'm done anyway.
Okay, either way. What about the the disruption cost?
Right.
That's the JJ.
Yeah, one comment I have is, when you are generating the user interface for the suboptimal case, you are using all the data that you collected for the subjects, right? Some of those subjects may be econs, as you say them. right? Making the optimal decision most of the time. And some of those subjects may be more suboptimal people that are making heuristic decisions.
Yeah.
I'm just curious if there was a way to understand which people are optimal and which people are not, and generating the model based on those people's data. I'm just curious if your results would be different.
Well, so of course I can look at the data and look at which people performed particularly well and which people didn't. You know, I can, for every user, I know his total score or the error rate for a particular user, so I know how well each user played. The assumption of, or the reason for training the model on all users instead of a subset of users was essentially the belief that the population we would get for the second experiment would kind of be similar to the population we would get for the first experiment. And there was no reason for me to believe if I only took the bottom half of the players from the first experiment that would give me the right model for the second experiment. You know, you should normally expect, okay, take all the data points you have, train a model that matches the data as good as possible, and that should be your best predictor for the second experiment. So what we definitely didn't do is take one individual user's behavior, look at how well can that user play a game, and then we re-optimize the game for that user. So that's not what we did. That was not, we didn't even try to do that. That would have required to let the user play for half an hour, take the data, re-optimize something, and then let him play the re-optimized UI. Of course, that should give you much better results because you are tailoring the UI to a particular user, not to a population of users.
Sure. The individual learning would definitely help in a model like this. But because at the beginning of the talk, you highlight the issue that there may be two types of users in the world, two types of players in the world. When you just get a model that is representing the whole population, you may just get a very noisy model that is not reflecting neither the econs or the noisy people.
Okay.
That's my concern about it.
So one clarification, when I talked about econs and humans, I didn't, so what I essentially meant is that no human is an econ. No human plays optimally and has unlimited bounded time and computational resources, but every human makes mistakes, and that's what we saw in the data. I agree that you could try to come up with market UIs, let's say with a set of market UIs, 3, and one is tailored for the very smart users, one for the medium, and one for the dumb users, and you could try to get other signals from users, either what do you know about this user, what do you know about this user's behavior on his phone, on his computer, and so on, to present him with a particular UI.
I guess a question might be, might this current data set you collected be useful to answer the question about whether there is likely to be opportunity for optimizing on a finer grained basis, or is it not enough data to do a type analysis at this point? Just if you had a whole summer to study this, take the current data set. It's kind of interesting to understand the value personalization that we do in search. I mean, for this kind of thing, it might be very interesting nuances in psychology. It might not be dumb or smart. It might just be more like the nuances of how they do like serial verbal scans of text versus bar graphs versus and so on.
I don't know the definite answer to whether the current data gives us, lets us answer that question. I definitely could look at that question. Yeah. I could look at the relative differences in performance between different users and look at whether these are statistically significant. I would predict that, definitely between the highest and the lowest performance there was, I knew how much I paid them. Some users I paid them $5, some I paid $42. So this $42 guy or woman made a lot more. Made a lot better choices than the other one.
For example, it would be interesting to know if $42 person versus the $2 person, what the gains or losses would have been per efficiency and per the optimization of the new interface.
Yeah.
For the diff between we saw before and after.
Yeah. So we could look at that. Yeah, it's questionable whether we get statistically significant results from that because that's even taking 20 users and now splitting them further apart. Yeah. Yes.
Since you gave people as many games as they could in a fixed time period, there was a mental trade-off between how quickly do I just, one strategy might be always just hit the topmost thing you can hit, and if it comes out any bit over 0, as long as you can do it fast enough, you should beat the other strategies and so on. Did you see?
Sorry, quick answer to that. So that was obviously a concern, and there's two ways we combated that concern. One is, I didn't go into all the details, but in the 4-minute game, after every game you played, we forced the user to make a 15-second break so that you couldn't skip ahead, so that you couldn't actually play an infinite number of games. But also, more importantly, I designed the game such that if you just clicked on the top or at the bottom or somewhere all the time, you would not, on average, come out with a positive expected value, because you really, the game was difficult enough so that a simple clicking strategy did not suffice. You really had to think. And that was that's what actually took me a lot of time and testing with interns, trying to design a game such that quick clicking strategy would not work. Yes?
A couple of questions I thought we'd reflect with the group about. What would it take to search through design space to come up with, to identify trades at the sweeter spot for design, do you think? Say we haven't found the sweet spot here. That doesn't mean that there might be a method, that might be a heuristic and or algorithmic approach to finding sweet spots. Any reflections about that?
I'm not sure I understand the question.
We said we
didn't find the sweet spot.
Right.
Yes.
So that raises the question: might there be a methodical way to identify
a better
when
way?
you're not in the sweet spot space, or find the sweet spot, besides just trying a bunch of things?
I think the first step should be the richer user model. I mean, that's also what I discussed with David Leibson. Try to identify all the factors of your environment that influence the error rate, such as loss aversion, such as possibly other effects that we haven't identified yet. And once you understand every factor that influences your error rate, come up with a user model that predicts errors as accurately as possible, and then that should give you better results. Yeah.
And then to echo Gideon's semi-humorous remark, which was, boy, what if this gets in the hands of the wrong people those strange people actually want to make profit in the world? Who are these people anyway?
Yeah.
And not necessarily help out the user. Might you have some comments on that? I mean, for example, might we as designers come up with incentives such that would not be possible?
So who's the designer?
Or mechanisms that actually make it in the favor of the owner of the interface to do things well for the user.
So
the competition that way it is. I mean, if
it's a competition also, yeah.
Yeah, because the user will switch to another provider.
So you're essentially asking if there's a meta design that we can, so that if we then give the methodology to somebody, they cannot misuse it.
It's a hard question, I realize.
I think one, I like to think of Amazon personal e-commerce. They really have the biggest experimentation platform for trying out certain things. Like, okay, what's the effect of tailoring choices to users' behavior to particular users? They have so much information about you, can offer you specific things. Of course, they can misuse the methodology by not offering you the choices that increase efficiency but revenue. And the competition, the best answer I can give there is the competition argument. If you, over time, figure out, okay, I'm not getting, I'm losing out, I'm going to a different platform, then Amazon has a disincentive to do that. Obviously, a big monopolist like Amazon, or not quite monopolist, but once you get really big, then there's a danger of the competition not working anymore. I don't see a way how you could build it into the design methodologies to prevent misuse of that method.
I've never said this to you before, but it occurs to me that it'd be really helpful for you to do at least some of your subjects eye-tracked. This next time you do the richer and have more choices, because I think you do need to go higher.
Yep.
Because once you start putting more and more choices, subjects really might not look at everything. They certainly might stop. We see this in search results all the time, right? They look at the top 2 in research.
Yep.
So you might really benefit from that, because then you'll see what they're actually looking at and paying attention to. And that could really influence. The attentional might be influencing more than you know.
And David Leibson has kind of studied this kind of thing of how far people get down in lists of various kinds of different lengths and granularities. And we talked about the idea of taking some of the, looking at search results with Sue and George's results on the heat maps to understand what you do.
That could have a huge influence on the design.
It's
as a factor.
Yeah, I mean, the eye tracking thing would be interesting. I wonder how much more that gives you in addition to already controlling for the number of choices, because
differently, I guess is what I'm saying, based on scan patterns of the eye. We even know people scan web pages in a very systematic, particular way, and we haven't accounted for that in this design. So I don't know why I never thought of it before.
People might be less likely to shirk, or they might be less likely, if they know they're being eye tracked, to go to skip things.
Yeah, that's true.
So you do have to.
If you make it tedious and onerous and
so the good thing in our experiment was we paid users based on how well they do, right? So they have a strong incentive to, whatever they're doing, however they're scanning things, do it in such a way as to maximize your money. And so I wouldn't be worried that they skipped.
For the amount of money, they still might not want to look stupid.
But it isn't necessarily stupid to skip over certain choices. If if there are 6 choices and I don't have time to read through all the information on the screen in 7 seconds, it might actually be the best thing for you to only read every 3rd choice or something like this. But I understand your concern that if you know I'm being eye tracked, then that changes your behavior.
We'll do it secretly.
Well, is that possible?
One issue is for some subjects, the cost of looking at all options and checking which one is best may be just costly in cognitive sense, that they may decide this value is not worth it. I'll just, choose one in a simpler way with using a heuristic. And that can be always an issue in this. And when it comes to the market design and collusion, I think it is not fair to compare the bandwidth market with Amazon just because there are contracts. So if you get into a plan, you are either there for 2 years, or you have to pay $500 or $600 to switch to another provider. And also the number of suppliers is much less, just because the infrastructure is big. So it is very easy for the providers to collude on implementing whatever is, providing them the best profit. Everybody implements the same thing, then you don't have a choice. These are 2 issues with the larger infrastructure.
But I thought in this room they say, if anybody, it would be you to come up with a plan to keep this honest.
That certainly deserves thinking about it, but I think the problem of generating the good incentives in this domain will be more challenging than the regular Amazon market systems. Just pointing out the difficulties.
I very much enjoyed your talk. When you showed the graph of the smoothly changing demand or supply or whatever was being modeled, I have to say, my head originally went to the air conditioner in my car. I don't think of it as a discrete thing. I either turn it up a little bit or I turn it down. Well, when I get in the car in the morning, I turn it way up. But I'm just adjusting a little bit. If we think about this, it seems like a natural view of this would be whatever choice I made, let's call it, if they're in order, C. The next choice for me is almost certainly, if I haven't changed, if only the market has changed and it's changing smoothly, is either to stay at C or go to B or D. A and E are out of the question because the market doesn't move very much.
Yeah.
And from a UI point of view, I think that's where I would always want to look. You want to pay, hey, things are getting tight. Are you willing to pay a little more to keep your current level?
Yeah.
Or things are getting loose. Would you like to upgrade? What would you like to do? And this discreteness, I think, isn't taking into account that context.
I think that's a good point. We got at that aspect a little bit when we studied this design level of changing choice sets, where we essentially, let me go back.
As long as it's anchored, as long as you can tell me, this is where you were.
Well, you sort of did that in the hidden market study too, Steve.
Right, I'm going to get to that in a second, to the hidden market study, but your idea I think is partly reflected in this idea of the changing choice sets, where we acknowledge the fact that it's a slightly different angle, but I think it gets at something similar, namely that here, if we know you're in a low importance task, perhaps we know that on average you choose something around 200, what we're going to give you are choices that are all around the 200 range, right? This is what this gives you, 0, 100, 200, and 400. If you are here, we know you're in a high importance task, and so we know that sometimes you choose the 1,000. So the analog to what you're suggesting essentially, if you're currently using something at 500, then your choice set should probably be 300, 400, 500, 600. And yeah, I think so. There, I think the motivation was similar for that design lever, but we haven't directly studied what you suggested.
He's suggesting that the cognitive overhead of making myopic changes that are in on smooth surfaces would be much lower, and therefore we might have to do less design work to optimize for cognitive costs.
Let me try
it actually
to.
goes down to something. Yes, stated more vulgarly. People are bad at making decisions. They're good at making adjustments.
Oh, what happened? Am I being kicked out?
You're finished.
Oh, no. Okay. Let me. I want to.
That's the electronic cane.
Oh.
Are you hooked up and everything?
Yeah, I didn't do anything.
I think it looks fine just now.
Yeah.
We have a Wizard of Oz behind the curtain that will help us if we have no problem.
Good. Let me get to the last two slides of this, and because I think this addresses partly your question, and it takes some of the ideas a little further beyond the study, what we actually did. So I want to remind you of this effect of changing prices. I showed you these results were statistically significant that when we have changing instead of fixed prices, the error rate increases and the decision time increases. So that's really, both is bad for social welfare. So what if we could avoid changing prices? And to an economist, that first sounds crazy because a standard resource allocation market requires that the prices for each resource keep changing up and down until supply equals demand, so until we reach an equilibrium. However, it's really tedious because prices have to change whenever demand or supply change to rebalance the market, or at least it has to change sometimes if we have this curve. And this means that if prices change, then also we need frequent user interaction with the market upon every price change. And that every interaction with the market is annoying to begin with, and then we've seen that interacting with the market with changing prices is even more annoying and is even more difficult. So what if we could hide part of the market from the users to avoid all of these costs altogether? And that's essentially the idea of a hidden market with fixed prices. So let's consider the 3G or 4G bandwidth market again. We have a fixed maximum amount of bandwidth that the market supplies, and every user has a variable demand, but with a fixed limit. I mean, you can't consume more than your cell phone can consume. There's a limit of how much of that resource you can consume, even if the price is 0. That's a strong assumption. It's not a valid assumption in other markets. If there's 0 price for Coke, I'm going to buy an unlimited amount of Coke, probably, almost. And furthermore, we need that each user has a fixed amount of some currency, either virtual or a real currency. So now the idea is we are going to keep the market price fixed over time, but we're going to expose a different set of the users to the market at different points in time to balance the market. So we will determine a market demand threshold T, and whenever aggregate demand is larger than T, then we will show the market UI with fixed prices to a subset S of all users. So as long as aggregate demand is less than T, nobody has to interact with the market. Aggregate demand rises above T, some users get a pop-up and are asked to make a choice regarding their speed now. Each user must make a choice, and some users will choose a choice less than the maximum choice, so aggregate demand decreases. The challenge is to find an algorithm that chooses the right size subset S and the right kind of users such that we can balance the market. And of course, the idea would be if today Kamal is chosen for the interaction to make a selection, then tomorrow he's not chosen and another subset of users is chosen, so that we are reducing the overhead on every individual user, potentially by n-fold, depending on how large a subset we take and how much we want every user to decrease his demand at a particular point in time. And we can still balance the market, but we keep prices fixed and they don't have to change over time. So it's a much easier task for the users to deal with. So in ongoing work, we're formalizing this design idea, and this is where I'm getting back to the efficiency question of fixed versus changing prices, which we can only answer essentially either in a simulation or in a formal model, because if you have changing prices, you can do more things than if you have fixed prices. You can more individually move the demand up and down more carefully than if you are showing a fixed price market to a subset of S users. However, you're gaining all this efficiency because you are not exposing the users to the market in the first place, saving their cognitive costs and so on. So this is the ongoing work that we're doing to compare these two design approaches.
Analogy with overbooking of flights might be useful there.
Mm-hmm. So yeah, this is something Kamal and I had talked about before. If everybody knows this scenario, you're at the airport and the airline overbooked the flight. There's 5 people that won't be able to fly among the currently booked passengers. And what should the airline do? Do we ask every user, okay, do you want to give up your seat for $500? Or that means every user is prompted with this information, sees that the airline has overbooked. Perhaps that's a negative signal or not. You can discuss this. But then every user is making this decision: is it worth it or not? And only 5 users at the end have to make that decision. So the analog is that you might only, if you have a model about users' values, then you might only show this decision to a subset of the users, such that you know on average, or at least 5 users will make the selection, and then you're fine. So we believe that this approach of designing markets where we're hiding a part of the market from a set of users can actually increase welfare significantly.
Do you think that will fly politically, those kinds of marketplaces?
Yes. Yeah.
You could say that, okay, you are our so nice customer, we are giving you first opportunity to earn $500. And they could know, the people who are travel on, let's say, higher fare, they might be
gold members of Alaska.
One second. To answer your political question, I have no worries about political issues here. Because I have already seen that depending on the browser you use to go to a credit card application website, you get different interest rates depending on the browser you use. That's like even crazy price differentiation based on your browser.
Firefox
yeah, Firefox browsers get the best rates. And this
You isolated that from the cookies that are in your browser?
I didn't do that study. Somebody else did, and I think they looked at that carefully. Yes. So this is treating users much more fairly than this, or much more equally than this browser-based approach, right? We're just randomly, sometimes you get the choice, sometimes somebody else gets the choice. And by the way, if you don't get a choice now, what that means is you get to use the market at full speed without having to pay for it, right? So you're actually not suffering. Okay. Did you have a question? Or?
Yeah, so I guess why is this different, say, than a Victory auction or something like that, where you make the decision ahead of time what your value is, and no one really has to answer anything. As long as the clearing price is 0, no one's paying for anything. The moment it goes up, you're paying whatever you put the value at.
Okay. Because if that would require, users' values in this particular market that we're studying are highly situation dependent, right? It depends very much on the current thing you're doing at this point in time, the email you're writing to which person, is your boss or your intern, how important is it, how time sensitive is it. So your value for speed is highly situation dependent, and I'm making the assumption that you cannot pre-specify your values for all possible situations that will come up in the future, such that, and that was the example with the Victory auction, where you specify your value once, and then...
I don't think it's any more ridiculous than assuming you know your value of what the next incoming email is.
No, you don't know. No. But what this approach allows you to do is simply use your application. Don't even think about what your value is for anything. And only if we ask you, and we will only ask you, let's say, once every 3 days, in that particular situation, do you now have to decide, what's my value for speed right now? And you should know that because you're doing something right now, and you have either that something you're doing is important or not important. So you only have to think even about what's my value for this if we're asking you. If we're not asking you, you never have to think about that value. Does that make sense?
Sure. I guess this is kind of going on already today.
I think that's very true, I think. But not because is it formalized.
Well, the carriers are already saying this protocol is more valuable. We're much more willing to interrupt your video than we are to interrupt your office VoIP or what have you. And so it's just separating the consumer one step away from if the service provider is making a set of decisions that conflict with your values, you may end up changing service providers.
It's locked in for 2 years.
Well, that's because they're hiding the fact that you can get out of the contract for $200, so you pay $500 for the phone. So you're not really locked in for 2 years.
Another hidden market.
Yes.
So, AJ, get a comment?
Just as a note, some researchers at BBN Technologies has been looking at a very similar mechanism for electricity market. I don't know if you know about it, but I think it's a very similar mechanism where if there's excess demand and there will be a blackout because of excess demand, they were thinking about sending messages to people, can you switch off your air conditioner please, otherwise we'll all have blackouts. And they were also thinking about who to send this message to.
Yeah.
You know.
And Todd's model would be that centralized, you have a preference model and a central control to lower people's thermostat temperatures from the power plant.
Well,
or raise them a little bit.
I send you a message saying, you know what you're doing right now? A minute ago it cost you $1 an hour, now it's costing you $4 an hour. What do you want to do?
Gentle raise of the temperature, right?
Yeah, so I know about these new electricity markets, and as you know, I'm studying this idea of hidden markets more generally for my thesis, and one application I started thinking about is smart grids and the question of how do we design these electricity markets and to involve the user at the end of the market in a proper way without overloading them with cognitive costs. Yeah. So
probably should summarize.
Yep, this is my last slide. To conclude, what we've done is we introduced this paradigm of market user interface design and the ways to look at it and study it. In this particular project, we studied these 4 design levers and ran the experiment. Here we saw the effect that we predicted. However, the drop at the end was not statistically significant. For the other 3, we saw statistically significant effects with respect to the error rate. However, the UI optimization, while it worked for decreasing the error rate, it didn't work for increasing efficiency. I offered some possible explanations for why that happened. Future work is a formal analysis of this hidden market idea that I just presented, and then also taking the idea a step forward, essentially to this long-term AI dream of the personalized shopping agent. Why can't I just let my agent do all the market interactions for me? Well, our motivation here was always the agent never knows my full utility function for every possible situation that I can be in. That's why we don't want to take all the choices away from the user. We want to tailor the choices in an optimal way for the user. But what if we could go a step further with the approach and essentially do an iterative or real-time UI optimization for the users when they are already using the UI? So that addresses Edge's question from before. If we actually know that this user is such and such good at making decisions, then we can really tailor the UI for that user. However, note that this requires some kind of feedback signal about how good the decisions are that the users make, which we get from our experiment. The question is, where would you get these from in the real world when you're no longer running an experiment? So that's an open question. And then taking this in another direction, how can we perhaps essentially put a Bayesian approach on top of this? What if the UI optimizer or your computer had a more sophisticated user model and sometimes it knows, okay, I'm really sure I got the value estimate right this time, and perhaps I'm even going to make the choice for you, not even going to bother you with the question, or I'm going to offer you just 3 very similar choices, like your idea, very fine-grained around the optimal choice that I think you will make anyway, or perhaps I have a really noisy estimate. I don't really know what your I've never seen this context before. I don't know what your value estimate should be. So perhaps I have to give you many choices in this particular situation so that you can make the best possible choice. And perhaps we can, take the smartphone idea again, if we can combine this with the wisdom of crowds, if I have many users in many similar contexts making many decisions, perhaps if I'm using collaborative filtering ideas, I can improve the market UI for user A based on based on looking at what all other users did in similar situations that are similar to me in other ways, behavioral or other ways. Okay, thank you very much for your attention, and thanks again to Eric and Kamal, Mary and Desney for a great summer and for being here. So, thanks.